Okay. I can move a few things along by talking about this now while we do this. Basically, I do end up doing a review of modulo math because when I've talked to people about it, saying, this is the basis of cryptography, and they're kind of like, yeah, I remember learning that. I think you do that in like the 6th grade, where you have remainder, like you do like 27 divided by 6 is 4 remainder 3. And at the time, I remember doing that, and I think it was about the 6th grade, and I was like, why would this ever be useful for anything? And I went to Boston University to get my master's in computer science, and I went, oh. My entire cryptography course was an intensely deep study of modulo, because that's what all the cryptographic algorithms are based on. They're based on the fact that if you say 27 mod 6, which is basically 27 divided by 6, whatever the remainder is from that, the remainder is 3. But then if you say 33 mod 6, you also get remainder 3. So if somebody says, I have a number, guess my number, if you do mod 6, you'll get 3. You can't know for sure what it's going to be, because it could be any number of numbers, right? Number 3. That one. Yep, I'll do. So imagine that you have these huge, huge numbers with hundreds of digits. Is it going to open? Let's get a lot of pictures in it. Pretty pictures. So if you have these huge numbers, and, oh, there it is, PowerPoint, yes. And then all you know is what the remainder is at the end of doing some operation with these numbers. It's impossible to know what the starting number was. And that's the basis of Diffie-Hellman, RSA, and also elliptic curve cryptography. So I just saved about a minute in my presentation. It's thinking very hard. Thank you for loading your laptop. Here it comes. It has a unicorn in it, my presentation. I thought it'd be nice to have a unicorn on Sunday morning. Oh, it's coming. It's coming. Oh, yes, there it is. This is actually the title of my presentation, is The Magical World of Elliptic Curve Cryptography, but I didn't want to do that in the submission to NolaCon because I was afraid they'd think I was like crazy, or that it would be all about like, the relationship between My Little Pony and cryptography. Thank you. Yes, thank you to the AV staff. So, excuse me, to flip the slides, I just tap. Is that going to work? Oh, thank you. Okay. All right. So here we are. My name is Michele Bousquet. A little bit about me. This is some things about me. I am from New Orleans, which means I have a lot of wigs and hats and tutus. And I also do some theater, and I like to put on an orange wig sometimes and pretend to be a Russian hacker and videotape things. And anyway, I'll give you my website at the end if you want to have a look at that. Anyway, when I got my master's in computer science, as I was saying, from BU, I had to take a cryptography course, and it was pretty intense, but I really did enjoy it because I'm a math geek. But then when I was trying to explain the joys of cryptography to other people, I found that they didn't get it. So I wanted to come up with a simple explanation of elliptic curve cryptography so that if you're an engineer or you're even just someone who's involved in the industry and one of your customers says to you, well, what is that actually? You can have a sort of intelligent answer to give them without having to spend 17 weeks deeply immersed in math in a graduate level cryptography course. So just a really basic thing. Cryptography in computing is used to transmit sensitive information. Probably, I don't think there's anybody here that doesn't know this. But basically, on any kind of device that's going to transmit information, particularly wirelessly, you want to be able to encrypt it before sending it off. This is a big part of app programming, for example. Now, when something goes through the air, the hacker can see it. So, of course, you want it to be safely encrypted before it gets sent back and forth. So, modulo math. I touched on this a little bit so we can buzz through this. If I say 27 divided by 7 is 3 remainder 6, the math way to express that is 27 mod 7 equals 6. That 3 we don't care about. We don't care about the 3. All we care about is the remainder. And you can see that if you go with sequential numbers, you will get your remainder moving sequentially. And also that if you're using mod 7, the only possible answers are 0 through 6, right? The answer can never be 7 because then it would be 0. So this also works with negative numbers if you need to do a modulo with it, but it's a little bit different. Basically, if you end up with a negative number, you keep adding 7 until you get something between 0 and 6. Basically, with any kind of mod 7, the answer has to be between 0 and 6. So it's kind of like having this box that all it has in it is 0 through 6. And you can take infinity, any number up through infinity, positive or negative, and it ends up getting stuffed into this box. Your answer will be 0 through 6. Okay, that's our little modulo refresher for those of you for whom the 6th grade is not a recent memory. Okay, so let's take a look at the way that this is more like the way this is used in cryptography. Now here, I've still got relatively small numbers, but we're going to do this with some bigger numbers just to kind of make the point. So suppose I'd want to do this math problem. 385 to the 57th power mod 293. You could probably get out your calculator and get an answer. It's going to be 89, because that's a forward calculation. No problem. But suppose you try to go the other way. You don't know what the power is. And you want to go this way, and you know what the answer is at the other end. Well, how do you figure out what x is? Well, this is what Misters Diffie and Hellman figured out back in the 70s, is that there's no formula for this. The only way to get it is brute force. So this is one of the cornerstones of the original encryption formulas. So the way that Diffie-Hellman works and various other key exchanges at a very basic level, and you've probably learned this at some point, but again, this is a refresher, is that me and you, we want to exchange some information securely. So we need to have the same cryptographic key, or at least corresponding ones if you were going to do public and private or something like that. So both of us need to, at our ends, figure out our secure key without passing any information between us that would expose, what happened there? It was like a magnetic field that suddenly appeared in my midst or something. Ghost, poltergeist. We need to be able to generate this key without passing information back and forth. Because if I generate a key and send it to you, the hacker could see that. You know, there had to be a way to do that. And this is, again, what Diffie and Hellman figured out. So what we do is we have a formula and we have some starting numbers. And those are in the middle. The hacker knows what those are. They're actually known. They're published. Everybody is using the same ones. But I have a secret number and you have a secret number, and we don't tell anybody what that is. And we have the starting numbers that we've exchanged. We know what those are. So we each do a modulo formula on it, and we get a result. So for example, I take 385 and I put it to the power of my secret number and do mod 293 and get 220. So the hacker knows the 385 and the 293, but he doesn't know my x. And you do the same on your side. So then we pass our remainders over, and the hacker can't figure out what that x is, because unless they use brute force. Then I take your result and my secret number, and I do another formula with them, and you can look up exactly the formula with this, but Diffie and Hellman found that I can take my secret number, get a result, send it to you, and take your secret, or your result, and do something with it with my secret number, and at the very end, we will end up with exactly the same key. And it's actually really cool. The first time I saw this, I was like, oh my God, that's so cool. And I took, I did like some 3s and 7s and 5s, very low numbers to try it out, because it is really interesting and very cool. Of course, if your numbers are very low like this, it's easy to brute force it, but the numbers that we're using here have hundreds of digits, and it'd be very difficult to brute force. So the hacker knows what the numbers are that got passed back and forth, but the only way they could figure out the key is to brute force it. So this is just how you would brute force a key. This is a very small table, but some hackers do make tables, lookup tables for known numbers, known prime, because usually using prime numbers, and some devices sometimes they're very lazy and they use like the same prime number that everybody else is using, and a hacker might have a table of that. But you can see where the tables would get really, really huge. So it's impractical for a hacker to have tables like this. Plus, if you are having a secure connection going on, the really good ones anyway, they will refresh themselves after an hour or two, or so half an hour, or some period of time. So new keys will get exchanged. And by the time they figured out your key, you've already got a different key. So ideally, that's the way it works, and it keeps everything secure. So all this is going on. Every time you go onto your phone and buy something on Amazon, all this is going on in the background. So RSA is a standard that's still safe to use. It's Diffie-Hellman, I don't think it's all by itself isn't used anymore. RSA has a little more complicated math going on, but it's the same principle. And it is safe to use, but every few years, NIST and other organizations start recommending that the keys are getting too small. If you want your devices to be secure 5 years from now, you need to bump up from a 1024 size key to 2048. If you want it to be safe past the year 2030, you're going to need to bump it up again. So the keys keep getting longer and longer and longer. And when they do that, it takes more and more power and more time to generate the keys and to do the exchange and stuff like that. Maybe it's only measured in milliseconds, but we also, at the same time, we're getting less patient. The other day, I went on to Waze, which I use for directions, and I hit Waze, and I had to wait 3.5 seconds, and I was like, what? Like, what? So then I went to Google Maps, and Google Maps only took like 2.25 seconds. I'm like, all right, I'm going to use Google Maps now. We're impatient. And also battery power. When you have a device, how frustrating it is, it weighs and everything, is it just chews up battery power. It's frustrating. So, before I get into what ECC is, elliptic curve cryptography, it is it's not a completely different method, but it's still the same idea of exchanging information where you and I can generate the same key without revealing anything to a hacker, but it uses a different kind of math. And just an idea here, these are the different key sizes for RSA and for ECC. And for a hacker to brute force one of these keys, look at the difference in the sizes. You can have a 138-bit key that takes the same amount of, that does the same job of a 1024. And smaller keys are faster to compute and use less power, especially if you're doing a lot of computing. This is going to make a big difference. And if you look also, as the RSA, the size of the RSA key doubles, the ECC key size does not double. They get larger at a lower rate. So as we're going into these bigger and bigger keys, the divide is going to be even bigger. Okay, so let's see, how does this work? It's fancy math. There's a lot online about this, and if you want to get in deeper into the math after seeing this, great, but at least this will give you a foundation. If you, like me, came to a certain understanding and said, okay, that's all I need to know about that, then that's good too. All right, so these are elliptic curves. Remember in math class, the teacher would give you a formula and you had to draw a graph. So this is the type of formula that they follow. Something squared equals something cubed plus something times something plus something, right? So these curves, these are their formulas. And they're really easy to draw. You just pick, start off with x equals 0, and, you get 5 and on the one on the left. And then you put in 1, 2, 3, 4. So you can draw your curve. These are really pretty looking ones that are easy to see, and the numbers are very small. The constants are very small. We got 3s and 5s. There's some pretty intense formulas for these, but they all follow that. And we're going to just look at a really, really simple one today to get the concept of how these are useful in cryptography. So we're going to look at this one, and this is my disclaimer. If you use this for encryption, you are an idiot. But it's really good for illustrative purposes. So we're only interested in integer pairs. We're not interested in any fractions or decimal or anything. And this is true for ECC also. So we have some pairs here. And notice that we have the negative ones. We have 1, 3, and 1, minus 3, 4 and 4, 9, and so on. So at some point, the graph goes nearly vertical with any elliptic curve graphs. Let's go back a little bit and take a look at those. See how at some point, they go nearly vertical, and you're not going to find any more integer pairs. So you need to just stick to the ones that you have that are within that. Okay, so here we have this curve, and we're going to perform modulo mapping on a graph. Oh my God. Bet you've never done that before. So the concept here is, remember we had that box that only contained 0 through 6, and all the numbers would get shoved in the box? We're going to shove everything into that part of the graph, the 7 by 7. So all of the points, the XY points, are going to be numbers 0 through 6. So you basically take the integer points, and going back a bit here, we have this negative point. See, 1 and minus 3. Minus 3 is not within our 7 by 7, but remember, for negative numbers, you keep adding 7. So that's going to end up being 1, 4. Got it? The negative 3, you add 7 to it, it's 4, and now it's in the 7 by 7 modulo box. So when we do that, we shove everything in there, and we end up with this in our little 7 by 7 box. Everything, all of the x's and y's are between 0 and 6. So these are our points. Oops. I went a little too far here. All right. So what we're going to do is look at these 2 points, 4, 2, and 6, 6. These are 2 of the points we ended up with. And we're going to draw a line between them. And then we're going to extend that line off outside of our box. And then, because it's outside the box, we can map it back into the modulo space. So we map it back into the modulo space, and there's the line. It's coming through here. Now, of course, there's programs that do this for you. Obviously, you're not going to sit there with a piece of graph paper every time somebody tries to, buy something from Newegg or something. It's a joke. God, you guys, man. Coffee. And then it loops around. You go back out and then loop it back around until you hit one of the other points on the curve. You follow how that works? Drew a line between 2 of the points, kept mapping it back into the modulo space. I see some frowny faces. Okay, let's go back a little bit. We're taking all of these points and mapping them into our mod space, our 6 by 6 mod 7 space. So every point, every line, everything that happens, we're just going to keep, mod 7 on every point that we get to shove it back in there. Okay. That makes sense? Okay. So we get this line, push it back in there, and we end up landing on one of the other points on the graph. So what we say, because we finally landed on another integer point, we say that 4, 2 plus 6, 6 equals 1, 4 in elliptic curve math. All right? So you start off with 2 points, and you do this thing, and then you end up with 1. And there's a formula for this. You can Wikipedia it. I knew this was going to be Sunday morning. I didn't want to hit you with that. But this is the basic idea. is that the addition operator means that. Okay? So the cool thing about this, wait for it. You can't go backwards, except with brute force. And that's the magic of elliptic curves, is that going forward, very easy. Figuring out what x is in this situation, really, really hard. What you would need is a table, just like you would need for modulo math, if you wanted to figure out what that was. If you have a complex enough elliptic curve, and there's like a dozen or so of them that are recommended for use for cryptography. This is not one of them. I'm telling you again. So it's the same type of thing. I have a starting point, and you have a starting point, and we both have a point that we're going to add. And the addition, by the way, is commutative. You can switch them back and forth. So I could, it doesn't matter which way you add them. You could say, A plus B or B plus A, either way. So I have a point, and you have a point, and then as a secret point that we have, and then we have a point that's known that we're going to add to it, and a curve that we're going to use so that we know our formula that we're going to use, and we both calculate, and we get our result, and we send them to each other, and the hacker can see the result, but he can't brute force what our secret one is. Then we do more math on the results that we got from each other, and we end up with the same key. So in this way, this parallels all of the key exchange concepts that we've used all along. It just takes advantage of the fact that with elliptic curves, when you have this thing about the 2 points and adding 2 points together to get a result, that it has the same quality of you can't go backwards without brute force. And it has the advantage of the keys are much smaller, and the calculation goes faster. So remember we talked about brute forcing keys when you're using modulo, the original type of modulo math. This is a really simple table for how you would hack ECC. You would need a table where this is the addition of, the points across the top and the points down the left. And then you have where the two of them meet. Like, everybody see what I mean? And some of them go to infinity, so you don't use those. A good algorithm won't let you use those. But the tables are, there's a mirror image aspect to it of it, where if you add, if you look across, adding it one way and adding it another way, you're going to get the same answer. But this is just 25 by 25 points. Now imagine if there were hundreds and hundreds, and the hacker had to calculate. So it's less hackable. So, so is everybody with me so far? Is there some witness? Okay, good, yes. So that's pretty much all I was going to say about how it works. And that's, at least gives you something that if you're at a meeting and someone says, should we use ECC or RSA? You could say, well, choose buzzword from my presentation and sound a little smarter and know a little more, Okay, so now we're going to talk a little bit more about how it's used and why you need it. So this is from MIT from February 2018. They came up with this chip that uses ECC, and it says reduces power consumption of public key encryption by 99.75% and increases speed 500-fold. And they actually already had an ECC chip that they had developed, but they actually put the calculation stuff on the chip. It's hardware-based now instead of software-based. So this was kind of cool. Now, I tried to find information on exactly which types of devices use ECC, but as you can imagine, a lot of companies are not too eager to discuss in detail what they're doing with their encryption. But I did manage to find some different situations where it's used. It's used in thermostats. The sensors for all the autonomous vehicles that are being tested, ECC is obviously very desirable because it uses less power, it's faster, it's very safe. You know, it's one thing to have your network hacked, it's another to have your car hacked. If someone hacks your network, probably you're not going to hit a pedestrian, or, you know, as opposed to the dangers, the physical dangers of it. And a lot of, you know, home security systems will use it. And most of the mobile devices have it available to apps. If you're developing a mobile app, you have the option of using ECC for your app, as long as you build it in. So that's basically why you would want to use it. It's more efficient, uses less power, better safety with smaller keys. And that's all I have to say about that today. And my next slide talks about me. As I mentioned, I sometimes put on an orange wig and talk about security, if you want to come to my website and visit me. I also have a password quiz to find out how much you know about passwords and what are good passwords. It's very simple. And also my email address to complain when you don't get a good score on the quiz. So any questions about ECC? Anything like that? Or are you guys all eager to get to the prizes? It's going to be drawings of prizes coming up. Yeah, we good? Oh, yes. What's that? Why no wig today? This is my first time presenting at NolaCon, and I was a little worried they wouldn't take me seriously if I showed up in an orange wig and started talking in a Russian accent about, you know, steal your password. You know, now that I've been here, and, you know, next year could be a little bit different. I might just submit with a picture of me in the orange wig and do a whole thing like that, but yeah. This is Svetlana. She has a lot more fun than me. She really does. Any other questions? Yes?
What would be the scenarios where you want to use RSA above ECC or hardware since it's more efficient, just as powerful or less supply within the rest?
The question is, why would somebody still continue to use RSA? Probably there's more support for it. It's more established. It's the easy way out. A lot of PC-based stuff still uses RSA because it's, you know, your PC's plugged in. The power consumption isn't as much of an issue. So the question was, from a theoretical standpoint, would you always want to choose ECC? I would. And I know that everything that I've read is like recommending it and pushing it. But it's, you know, you got people who've been doing this job for 10, 20 years and everything is very familiar and they don't want to have to move into something else which they have to support and be responsible for. So it's, you know, it's going to either take some time or take some pushback from the industry where there has to be some serious RSA fail or something before it's going to be. But it is being used more and more. And, I mean, one of the things is that consumers don't understand the difference. So, for example, there was some recent thing where, not so recent, but the Belkin home security devices turned out to be easily hackable, and they were all using RSA. So, when I would buy a home security device, I would want to know it was using ECC. But, you know, my other family members who aren't in InfoSec don't care. All right, any other questions? Yes?
So in ECC, there's multiple curves. Which elliptic curve do you trust the most?
I do not have an opinion on which elliptical curve to trust the most. I know that NIST recommends like 15 different ones, and I don't have enough practical experience with it to really answer that question. But I would, you know, it's easy enough to find which ones. And also, following the advice of my cryptography professor, where he said, don't ever try to write your own cryptographic function, just because it's just always a bad idea. There's other people who've devoted their life to this, and they have teams of people testing stuff. So there's already modules out there that have been found to be safe and secure and everything, and you would just end up, you know, like with any language, there's going to be a, you know, some function somewhere or some module that you can include that is going to include all that, and you just have to get it into your code and working. So that's a great question, though. I should find that out for the next time. I can present my favorite elliptic curve, and I could draw little hearts and rainbows on it, things like that. All right, anything else? Anybody, any questions? Who wants to win things in the drawing? Oh, come on, that's an easy question. All right, thank you very much.